Welcome together. Today I want to show you how we can control with the nRF54L15 developer kit, I²C bus, and especially a little bit more complicated sensors, the BMP388. We could use a library or a driver, but this is not how I want to show it to you. I want really to go into the details. We look at the data sheet, how to program it, and how to calculate the pressure and so on. So the BMP388 is a temperature pressure sensor, so actually mostly pressure sensor. The temperature is just needed to calculate sensor pressure. I'm using here the board from Adafruit, so BMP388, the stemmer with this connection, but we will use the pins here. We have to make a few preparations. The first thing is that this sensor needs a little bit more voltage than the default voltage on the board. When you're looking here, we have to power it with 3 until 5 volt. There's a voltage regulator, so V in has to be at least 3 volt. And like I showed the last time already, the default configuration from the nRF DK is smaller. So we open the board configurator. In checking, I already changed it, but I want still to show it. So you go here down and checking the voltage. I have here already 3.3 volt. The default is 1.8 volt, and this would not be enough for powering this sensor. So just select it and then write the config when you have connected already the board and you have the supply voltage. Like usual, I'm starting with a blinky example. I just copy it and name it BMP380 nRF54L15-DK. I have to delete the build and then open it in Visual Studio. We just add the build configuration, and then we are selecting the right board target. The last time I selected, not really the wrong one, but not the right one. You have to check here. You can emulate also the smaller nRF54 series, so the L05. The last time I took this one, we want to use nRF54L15, which is actually on the board. Yeah, just generate and build it first. When the build is done, first we have to activate the I²C. This is done in the project conf. I will copy this first. Just activate the modules, config I²C to yes, and I use also the floated point print again, so I make this also to yes. With this, we activate the modules for I²C. The problem what we have now is that with nRF54L15-DK, I²C is default disabled. So, and this is a little bit complicated to find out actually. We go in the Devicetree and Is it on the right one? Yeah, save here. Devicetree. And searching here for I²C. And you're seeing this one here, I²C 20 is disabled, I²C 21 is disabled, and I²C 22 is also disabled. So no one is disabled, and also no pin configuration is done here. So what we have to do now is to add this in the overlay file. So we're going here, we select our build. So this is why we have always to compile it first. We're going in our configuration files in Devicetree and clicking here on create overlay file. I'm not build it yet because we didn't write something inside. And in the overlay file, we have to define the I²C to activate and also to configure the pins. Yeah? So I use I²C 22. I disable it, setting the I²C 22 default pins and the sleep pins. And I also configure here already that the BMP388 is connected. Yeah, I just say it's an I²C device, say status OK, and the I²C address is hex code 77. Yeah. I will show it in a second also in the data sheet. The pin control we have also to set. I using here for SCL GPIO port 1 and pin 11, and for SDA 1 GPIO 1 and pin 12. And this is also for the sleep. Yes, this is actually the default values which you use normal for the I²C bus. Yeah, when we have this, we can continue making a pristine build first. And when this is done, we can start programming. The I²C address, which we are using, I just said it, it's hex code 77. You've found this in the data sheet from the BMP. There you have, when you're looking here, that 7-bit address is in binary this one. The X here is depend on if the SDO connection is to ground or to the voltage VDD, and this is default with the Adafruit board. Yeah, so we have hex code 77. We have also to connect our BMP board with developer kit. We have here voltage in, ground, the clock line from I²C, and the data line from I²C. And at our board, we have to connect it with GPIO port 1. Here you're seeing our board. We are using the VDD from GPIO port 1 and also the ground here. And here, when I tried it the first time, I fall a little bit. I tricked myself, actually. I connected it to 11 and 10 because I just thought, just click it inside, but you have to be careful. We defined here 11 and 12, so we are using these 2 pins here. Yeah? So the clock line goes to, where did we define it? So overlay file, the clock line goes to 11 and the data line to 12. On our board, it looks, of course, like this here. Yeah, we're having here the GPIO port. Here's an 11, here's 12. And on the other one, on the BMP, we have to connect it here. Now comes the fun part, the programming, and when you do it really manual without any driver or library, it's really not so easy for beginners, but we will start slowly. So you're seeing here we have register 00, and there is standing the chip ID. So this is the first thing what we will read out. The chip ID is 50, so we expect to getting here the 50. And for this, first in the header, we include the I²C part and the print K. And afterwards, we needing the chip ID as macro. And the chip ID itself or comparable is 50. Then we need, of course, our device. We have here our BMP node, which we defined in the overlay file. We are using the label BMP388, which I defined here. And then I get an I²C structure, which stores actually the I²C address and the device itself. So we can easier use it and don't need to define the I²C address again. So starting with the first step is checking if the I²C bus is ready. We will make here first define an error variable, then making device is ready and taking I²C def, which we defined before the structure, the bus. If this device is not ready, we print out an error code, and if not, that the I²C bus is ready. And in the next step, we're checking the chip ID. And this function is actually not so difficult. Using here's the function, and the function just sending the register, the chip ID register, which is 00, and store then the return byte which we get into the ID. And there is a function which is called I²C read dt. It just needs the I²C dt spec, and then sending 1 byte and reading 1 byte. We're sending here the register and reading out 1 byte here with the ID. So there's an error, we print out that something went wrong, and then we're checking if the ID what we're getting is the chip ID. And this we can already compile and run on our device. And on port 12, I will reset it. You're seeing here that the I²C bus is ready, and also the chip ID is 15 hex code. So now the preparation is done, and we see that our device is reacting, but we cannot just read out something. In default, the sensor is in the sleep mode. We have first to set the register, the power control register, which is on the register 1B. This is a power controller. There is a mode, and also what we want to measure. And we want to measure the temperature and the pressure. So we have to enable this. And the power mode, we're having here 3.1. So it's the sleep mode, which is the default mode. So when you would read out something now, you wouldn't get any data. You have a forced mode where you then get one time something, one measurement, a single shot, and the normal mode where it's always measure something. Yeah. Okay, for this we define a few registers again. Actually only one. The power control register. And in the next step, our main, we using the function enable. After checking the chip ID, we enable the sensor. If something is wrong, of course, we print an error code. The function itself is also not so difficult. Here we have the function, copy and paste it. So we're setting the power control to a hex code 33, which is a binary syscode here, and we just saw it in the data sheet. So this means that here the temperature sensor is on, and bit 4 and 5 is also set to 1, so normal mode. We're making just and right, we are writing this error with the power control and the value, so 2 bytes, and waiting 10 milliseconds that the sensor is powering up, and then our sensor should be ready for reading something. Now we can read out the register for the pressure and the temperature. You're seeing here we're having 3 for the pressure bytes and 3 bytes for the temperature. It's starting with hex code 4 and going until hex code 9, so 6 bytes altogether. And there we define again the register where we have to start the reading, which is 04, and we will read out then 6 bytes. The function for reading out this bytes is read raw data. So we're starting with a register 04. We are having here an array where we store the values, so 6 bytes. And then we're just making I²C write read. So first we're setting the register here where it's starting the bytes or to 04, and then we read out 6 bytes. And we will store this value in a variable which is called BMP388 data, and call it raw pressure and raw temperature here. And this data type is a little bit more complicated. I copy it directly all, but we will not use it as a parameter yet. I will explain the others later. So you're seeing here our BMP388 data, and we're having there raw temperature and raw pressure. And now we can read it out in the main. in the while loop here. And build it flash it to the device. And you're seeing here, you're getting a raw temperature value and a raw pressure value. Yeah, only that's the result from the pressure and the temperature. The raw data are not helping us a lot. We have to calculate the compensated temperature and pressure. And this is a little bit complex. We're having here calibration registers or the trimming coefficients registers. So they are starting from hex code 31 and going to 45. So we're having here values non-volatile memory as NVM parameter T1 until T3. This is for temperature, and then pressure 1 to pressure 11. This is the first step what we have to read out. And for this, we need again macro to define the calibration part, where it's starting and where it's ending. So here we're starting from calibration register 31, and these are 21 altogether. And you see already I defined the structure. This parameter which we are reading out, the NVM trimming registers, are stored also in the structure BMP388 data. And the function for reading it out is here. We place it after enable the sensor here. And you're seeing what's happening is, again, we're having here an area which with a length from 21 bytes and the starting register, and then we're sending I²C read. So we're sending 1 byte again from where we want to start to read, and then we're reading the 21 registers and store it in the array calibration calib here. And when we read this out, then we're starting to store the parameter in our structure here. We're having then NVM part T1, parameter T1 to T3, and P1 to P11. And then we print it out here for checking if we're getting the data. We have, of course, set it then this function in the main directly after enabling the sensor. We have to make this only once, so the value are not changing. This is different for every sensor, every BMP sensor, the calibration data, but we have to read out it at least once. Yeah. Okay, then we can build it again. Flash it to the device. And here you're seeing the values. Would be nice if we could use just the calibration register directly, but this is not the case. When we are looking here at the, we have here the compensate function for the temperature and for the pressure, but we cannot use directly the parameter which we read out before. We have to calculate before double values with this formula, yeah, which is yeah, again a little bit work to do, and there I make the function calculate trimming coefficients. So, and this function just makes the whole calculations there. I have it. Yeah, it's a lot of fun. Yeah, this is the function. I place it directly after the function for reading the values. And you're seeing here, I have two helping variables, yeah, temp1 and temp2. Mostly I'm needing the temp1 variable, but sometimes also temp2. And you're seeing what's happening here. Here we have to divide the NVM parameter T1, so this value, and when you're seeing the function, yes, this is actually what's happened. I store in the temp1 variable just 2 power -8, and this is the value. And then for calculating, I'm making just this calculation, and this is happening with all the part. Yes, the next one is then 2 power 30, then 2 power 48, and sometimes we're having two variables with the P1, for example. So I have to make minus first with 2 power 14 and then divide it to 2 power 20. And yeah, this is like you're seeing here, P1 and so on. This is what's happening here. Yeah? And also the data structure, what we're having, I have then here the parameter T1, T2, T3, and P1 to P11, and all as double values. Yeah? Now we can go to the next step and calculate the temperature, yeah? Compensate the temperature. The function is standing here in the data sheet. And we're starting really with the temperature because it's a little bit easier. It's just this two calculations, and then with this calculation we're getting out directly the compensated temperature. So see, it's not so complicated, the functions this time. I just store it here. BMP compensate temperature, having here our variables, and here's a calculation, so two calculations, and here's the third calculation. We're getting directly the compensated temperature, which is stored under BMP388 data here. I don't know why it uses if it's from linear or something like this. I take it from the data sheet. I could also call it compensated temperature or whatever. So we have this also in the BMP388 data structure. And of course, we just have to calculate this in the main function. And we're coming slowly to result and to the end. So we check this first. Flashing it to the device. And you're seeing that we're having here a temperature. Yeah? When I put my finger on it, you're seeing also the rising from the temperature. So this is actually already a quite success. And in the next step, we have to make the same for the pressure. That's the function. And the function itself, when you're looking in the data sheet, it's a little bit longer because we have also more parameters, and also we have to use compensated temperature, TLIN here. This is why I keep the name. And the function itself is here. Now we can build it. And flash it to our device. And you're seeing that we're getting here also the pressure in Pascal. Yeah? Actually, I like to understand how a sensor is working and also to having the control about a sensor. But of course, there is also a driver in Zephyr. We could use this one instead. Yes, then I'm making here in the overlay file, instead of I²C device, I say it's compatible with the Bosch BMP388. And in the project conf, we have to configure first the sensor module to yes, and also config BMP388 to yes. Now we can get rid of the whole complex source code. We just have now a short source code, so we're needing the sensor driver. We're getting the device from the node label, and then we're checking if the device is ready. If it's not ready, if it's ready, then we're making a sensor sample fetch from the BMP388. Then we're getting with the sensor channel get the ambient temperature, with the sensor channel get also the pressure, and then we print it out with the sensor value to double. So this is how it's working with the driver. We make a pristine build. Then we flash it on the board. And seeing that the device is not ready. I had a little bit to search. It seems like we need also a few parameters here that it's working. So I had to add this parameter in the device tree. I'm making again a pristine build. Flash it on the board. And now you're seeing that we're getting the pressure and the temperature, this time the pressure in hectopascal. You saw now how complicated it can be to getting a sensor to work and going through the data sheet. I think actually it's important to know how this works sometimes. Not every time you're getting a driver, and sometimes with a driver it's not like you want that it's working or something, or you need special things from the sensor which is not implemented in the driver. Yeah, with the driver, of course, it's really comfortable if it's supported, and you get it quite fast to run. So see you in the next video.